So that's the basic result we wanted to get at. So just to go over it one more time so we make sure we got it. We are defining this ballistic conductance as Q square over H times a quantity we call M. And at this time we have no particular reason to do it this way, but what we'll see is the physical meaning of M. That's what we are coming to. Right now all we are doing is some algebra. We're saying, okay, let's call that M. So M over H looks like what I had before, 1 dimension, 2 dimensions, and 3 dimensions, and those factors come from averaging velocity as we discussed in week 1, and it's worked out in one of those tutorials from week 1. Okay. Next, we use the fact that the relation we had earlier this week, possibly the very first module of this week, that dVp is equal to n times the number of dimensions. So instead of dV, I put in n divided by p, and this dimension we took account here. Okay. Next, we say, okay, so this is the expression for M, but we have an expression for the number of electrons, this n already. It looks like this. So let's make use of that here, and that is how we ended up with this expression for the quantity M that we have defined. Now what I want to point out is that now that we have this expression, it gives us a sort of interesting physical viewpoint about what M means. Okay. So think back about what this number n means. The way we obtained this expression, and that was in module 2.2, I believe. In module 2.2, we obtained this expression by saying that, well, if you have a solid, 1D, 2D, or 3D. Question is, how many of these wavelengths can you fit? So supposing you had something which has like a two-dimensional conductor. So W one way and L the other way. So question is, well, how many wavelengths could you fit in? Well, it's proportional to the area, WL, and then you get pi WL times this P over H, which is like the inverse of the de Broglie wavelength. You see, H over P is like de Broglie wavelength. So it's like WL divided by lambda square, right? De Broglie wavelength square. So what it tells you is how many wavelengths fit into that overall area. If you have a three-dimensional solid, well, it's a question of how many wavelengths fit into that overall volume. If it's one dimension, well, how many wavelengths fit into the length? Now, if you look at M, it is like one dimension lower. So if it's one dimension, well, M is just one. So when you have a one-dimensional wire, the quantity we have defined as M is just plain 1. That's it. When you have a two-dimensional thing, then this quantity M is proportional to the width. And what it tells you is how many wavelengths fit into that width. And in 3 dimensions, that is, you have a solid like this and current is flowing this way, what M tells you is how many of wavelengths fit into that cross-section of the wire. So in 3 dimensions, N would tell you how many wavelengths fit into the entire volume. But M would tell you how many fit into that cross-section. That's why it's proportional to the cross-section. And that's the meaning of this quantity M, really. That it is, in a way, it tells you basically then that when current is flowing in that cross-sectional area, how many wavelengths fit in. And that's what you call the number of modes. And those of you who have some familiarity with electromagnetic waveguides, you may recognize the word modes. But if you are not familiar, don't worry about it. But that's where the word modes came from. Now, why do you expect that to be an integer then? Well, as you might expect, that this is like the number of wavelengths that fit in. And of course, when you're trying to fit in wavelengths here, it has to be either 1, 2, 3, 4. If you fit in like 10.5 wavelengths into a cross-section, then of course, that would be a mode that would not be allowed. So usually, the number of modes is the nearest integer. That is, what I mean is, if when you calculate this, you get say 10.5, then the correct number m would be like 10. It's like the 0.5, that mode wouldn't be there. It would be like 10 of them. So the correct expression would be like the integer version of this. And this is what, of course, if you are using a wave equation to describe your electrons, this is the part that would come out naturally from the wave equation. That is, the fact that it is an integer. But in our argument, the way we are thinking about it is that, remember, the way we found n, the same story here, that supposing we have a certain, let's say some momentum p, and these are the allowed values of momentum, and you're asking how many of these allowed values are contained in there, and that's what tells you the number of modes. The point is, it would either be, say, 7 or 8 or 9. It cannot be 8.5. And that's why it's an integer. And this interpretation, of course, only becomes apparent once you write the modes in this form. You see, because if you go back to our original definition of the way we started, we said, well, what is the number of modes? Well, it's proportional to the density of states times the velocity. And then you see, there is no good reason to expect that it will be an integer. And so these are these two very different ways of thinking of modes. One is density of states times velocity, which seems natural when you say that, well, you have a certain number of states, density of states tells you how many electrons there are, and how much current you get depends on the number of electrons times velocity. So it seems natural that when you're talking of conductance, what should matter is density of states times velocity. But there is no good reason to think that that quantity would then be quantized. Unless you can make kind of, once you know the answer, you could try to make heuristic arguments like saying, well, this L over V is like time. It's like the uncertainty in time, and the density of states is like the uncertainty in energy. And so the product of the uncertainty in energy and time should be h. But that's not a convincing argument. It's like something, once you know it, you could rationalize it probably that way. But the way you can see why it's an integer is, if we use the models we developed this week and rewrite that quantity in this form, so that you realize that that quantity can also be interpreted as the number of wavelengths that fits into the cross-section of your conductor. And so if your conductor is one-dimensional, the answer is just plain 1. And so the ballistic conductance then would just be q squared over h. If it's two-dimensional, then what you have to do is look at the width, see how many wavelengths fit. If it's three-dimensional, look at the cross-section, see how many wavelengths fit. And that will be the way to interpret this new concept that we introduced in this module, this m, or the number of modes.
Check it out now, y'all.
NanoHub U, online instruction.
Well, welcome to the last module for this week. And if you remember, what we did for the first 4 modules was we worked with the expression for the conductivity in diffusive conductors. And what I tried to show is how you could adopt a specific model and have a way of calculating this density of states. And we use that to relate it to the Grood model for conductivity that is widely used. So that was kind of what we did for the first 4 modules this week. In the last module, we started with talking about this ballistic conductance, because one of the nice features of this way of describing transport, the one that we introduced last week, is that both the diffusive result and the ballistic result all fall out simply from the same viewpoint. And we had this expression for ballistic conductance, and what I said is, let's say if you write it in this form, with number of this quantity as number of modes m divided by h, what you can show is that m can be expressed in this form. That is, what we did was we had this expression for total number of states up to a certain momentum p, and this is like the total number of m up to a certain momentum p. And what I tried to explain was how this represents like how many wavelengths fit into the box, while this represents how many wavelengths fit into the cross section. And from that viewpoint, I mean, if you just rearrange this a little bit, you obtain the expression I've put up here, which is m for one dimension is 1, 2 dimensions depends on how many wavelengths fit into the width, 3 dimensions, how many wavelengths fit into the cross section. And then I argued that these things in 2 dimensions and 3 dimensions, you'd think, would change continuously. That if I made the conductor wider and wider, this number should increase proportional to the width continuously. And in that case, you would expect that the ballistic conductance should also be proportional to the width. But once you adopt this wave viewpoint, that basically this is like the number of wavelengths that fit in, then this you have to take the integer value of this. So then you would expect that when you increase the width of something, the ballistic conductance should go in steps. That is, this m could be like 1 for a while, and then it becomes 2, and then it becomes 3, and 4, and 5, and so on, but does not go as like 4.7 or 5.8. It will go in steps. And this is the seminal experiment that was reported again a little over 20 years ago, back in 1988, which I have shown in that slide on the left. Actually, there were 2 separate groups that reported it around the same time, back in 88. And what it showed was an experiment which was done on a conductor